All right, so we're very happy to welcome back Susanna, who just joined us as a new postdoc. She's going to tell us about black holes and weak Jacobi forms. Take it away.
Awesome. Yeah, I'm very excited to be here and to get to know all of you. And yeah, so today I'm going to talk about black holes and Jacobi forms and how they are connected to each other. And this is based on a paper that came out over the summer that I wrote together with Luisa Polo, who's at BIMSA, Alejandra Costo in Cambridge, and Diego Lisca, who's now in Switzerland. And before we start, I should say two things about this project. It was really a lot of fun to do. And one of the reasons was that there were like a lot of very different puzzle pieces that all came together in a very nice and intriguing way. But unfortunately, I won't have time to discuss all of them. So there's a lot more going on behind the scenes, and I'm very happy to talk about any of that at any time. And then the second thing is that there's a lot of technical details hiding behind the curtains. I'm gonna try and not talk about technical details as much as I can, but there will be some stuff that's a little bit dry. Again, I'm happy to expand, but really today I'm trying to get the physics message across as much as possible. But feel free to ask questions at any time if anything is unclear. So we're talking about black holes, and hopefully this formula looks familiar to all of you. It's the expression for the black hole entropy. There's this universal term that scales with the area. And what's remarkable is that it doesn't matter at all what theory you're looking at. If you want to know the entropy of the black hole, you just compute the area, and that's it. And then the first correction, first possible correction grows with the log of the area. And it comes with a coefficient that's theory dependent. So it depends on the fields and the stuff that you include in your theory. And today I'm going to talk about this number for the whole talk. And what we'll try to do is to explain that number from the microscopic theory. And to do that, we will use the connection between black hole entropy and modular forms. And in that setup, we will be able to give a precise microscopic interpretation of that number. And in the process, we will also learn about the microscopic description and precisely which are the states that go into this number. All right, so here's the outline of the talk. I'll start with some setup and a summary. So if you're tired, you can just pay attention for that part and then zone out. Then I'll talk about the actual forms that we're going to discuss, called weak Jacobi forms. We'll discuss asymptotic expansions, and then we'll go to some examples where we can apply the techniques. And they come in the form of symmetric product overfolds. And once we've understood those, we can go to gravity and really see where this coefficient A graph comes from. So let's get started. The setup that we will consider is that of BPS extremal black holes in 4D and 5D engaged supergravity, which are characterized by some charges. So here I wrote the path integral that computes the partition function. This depends on the values of the charges, and you integrate over the metric and matter fields in the theory. And at large values of the charge, we can perform this path integral via saddle point approximation. And when you do that, you find our favorite formula. And the way that you take the charges that you should take the charges to scale is how I wrote here on the right-hand side. So the way that you define the scaling regime is by introducing a parameter called lambda. You take that thing large. And when you take that parameter lambda charge, you want large, you want the charges to scale in that way. And when you do that, the area scales with lambda to the d minus 2. And once you do this whole machinery and you perform the path integral, there are two sources for the logarithmic correction A graph. One contribution is from zero modes due to isometries in the solution. And there can be some local contributions for massless modes in the theory. And the way that you compute these is by doing a one loop determinant around the classical saddle of the path integral. All right, so that's basically all I'm going to say about the gravitational computation. And from now on, we'll focus on the microscopics behind this formula.
So what are the like isometries here in the last?
Yeah, they're like symmetries of the geometry.
Yeah.
And possibly like gravitinos and things like that. Oh, wait. And in these setups that I just discussed, the BPS states are counted by modular forms. You can think of, I'll be more precise later, but you can think of them for now as a function of tau and z that has a Fourier expansion with coefficients C and L. And this is an index whose Fourier coefficients are equal to a trace over the Ramon sector of the microscopic theory behind the gravity theory that has these black holes. And what's inside of the trace is a signed count of quarter BPS states. And at large values of the charges, these coefficients can be computed, and they are given by an expansion that looks like this. Here, delta and delta naught are variables that will turn out to be very useful to analyze the coefficients at these large charges that we're interested in. And just like the gravitational expression, there's a universal piece that once you translate it back to the gravitational variables corresponds to the area term. And then there are two possible sources for logarithmic corrections from taking this delta large, and also there can be a logarithmic correction due to taking delta zero large. I'll make this all more precise later. But the punchline is that it was found by these people that the logarithm of these coefficients at large values of the charges is equal to the black hole entropy. And so our goal for today is to revisit this equality and to really understand where does it come from in terms of these coefficients A graph, A delta, and A delta naught. All right, very good. Let me now be a little bit more precise about what we're going to do. So we'll discuss weak Jacobi forms. In weak Jacobi form, it comes with two parameters.
Two questions. We're in 4 or 5D, right?
Hmm.
How are we working with it? Where is the absorber coming from? I will not see central charge. Where is
in these setups, the black holes, when you go near extremality, there will be an ADS2 times S2 horizon or geometry emerging. And in the cases that I'm discussing or that we'll focus on, you can uplift those to an ADS3. And that's where these CFT2 type things come from. Right, so weak Jacobi form, it comes with two parameters, a weight that we will call K and an index called T. And it's a function from the upper half plane times the complex plane to the complex plane that has a Fourier expansion of the following form, just like on the last slide. Here, N and L are integers, and these coefficients, they are 0 for all negative N. And here n, you can sort of, in CFT language, see it as a scaling dimension, and L is a charge. Furthermore, weak Jacobi forms, they have very strong properties on their transformations of the modular group, where the modular transformations, they depend on these parameters K and T. And they also have nice properties under elliptic transformations, which in more physics language means that they encode spectral flow symmetry. Very good. And we can organize the states in a very convenient way using the so-called discriminant, which is this particular combination of the charge, of the different charges and the index. And if you analyze the transformation properties, the modular transformations and the spectral flow transformation, it follows that the Fourier coefficients only depend on this discriminant and the charge not 2t. Moreover, the discriminant allows us to organize the states according to the value of the discriminant, and we will call states polar if the discriminant is negative. You can think of these as light states of the theory, whereas non-negative discriminant states are called nonpolar or heavy. Very good. And so when we are looking for black holes, usually we are taking the discriminant to be positive and large. Furthermore, the discriminant is bounded from below by this value that I will call delta 0. We will parameterize it by an integer called b. B should be less or equal than the index. And one assumption that we will make is that the most polar state has 0 scaling dimension, which is very natural from the CFT point of view. And that most polar state will then have a charge equal to plus or minus b. And the nonpolar or heavy coefficients of weak Jacobi forms are related to the polar or light ones through the so-called Rademacher expansion. That's a mathematical result that gives you the nonpolar C's and writes them as a sum over the polar coefficients or the light coefficients. And those coefficients are multiplied by some pretty complicated combination of functions that we can compute. And so in this way, you can relate the heavy states to the light states. And one important thing is that the Rademacher expansion, it encodes all the symmetry that is there in a weak Jacobi form. So it encodes the whole modular group and all the elliptic transformations. And this thing on the right is called a Kloosterman sum. It will not be very important today, but it's a well-defined function that you can compute. And already from this Rademacher expansion, we can see where the area growth originates from. And that's from the Bessel function that appears. Because at large values of the argument, the Bessel function will grow like an exponential. And so when you look at the Rademacher expansion and you figure out what is the most dominant contribution at very large values of the discriminant, where we expect large black holes, then the leading contribution looks like what I wrote in the bottom, which is precisely the translates to the area over 40. However, to make the comparison to gravity more transparent, the Rademacher expansion is not very convenient, because to go to a semi-classical limit, you have to make the index t very large. And in that regime, this combination of functions becomes very complicated to evaluate. You could do it, but in some sense, you have the data that you have is too fine-grained. You want a more, or we would like to have a more coarse-grained expression so that we can very explicitly see what is the data that goes into the first logarithmic correction to this leading order growth behavior. And so for our purposes, it will turn out that it is very useful to use this thing called a crossing kernel. And the crossing kernel, it again encodes some of the symmetries of the Jacobi form, but not all of them. We will only encode very explicitly the S transformation that relates heavy and light states. And the way to derive it follows very naturally from usual standard statistical mechanics. First, we write the Jacobi form as an integral over a density of states. And here, this rho should be seen as a sum over delta functions that is multiplied by the coefficients that showed up in the Fourier expansion. And I should make a small disclaimer that this isn't really a density of states because the coefficients can be negative, but for all intents and purposes, you can see it as a density of states. And using an S transformation on the right-hand side, we can replace tau with -1 over tau and z with z over tau. We include the transformation factors coming from the weight and the index that showed up in the modular transformations. And then you get this expression, which doesn't look like much yet. But once we do an inverse Laplace transform, we arrive at the following equation called the crossing equation. And it relates the density of states at some energy and charge to an integral over the full density of states multiplied by this thing that we will call P. And this equation is called the crossing equation because it relates different energies and different charges to one another. And this object called P is the crossing kernel. And we can solve for this crossing kernel analytically. It's given by the integral that I wrote there. That integral, you can solve it. And once you do that, you get, well, an answer. And once you look from it from afar, it already looks a little bit like what we saw before with the Rademacher extension. Again, there's a Bessel function. The argument of the Bessel function is the same. But the difference is that this function, there's no sums, there's no complicated Kloosterman sums included. So this is a very computationally friendly and more coarse-grained object.
Is the energy somehow related to a delta, or?
Yeah, in the same way. Or you mean the discriminant delta?
Yeah.
Yes, so it's in the same way. Figure out where I wrote it. Sorry. Right, so this row with the energy is related, the energy is related to N in this way, and J is related to L through these delta functions. And so delta was given by N minus L squared over 4T. So in this way, again, you can imagine the same expression for the continuous variables E and J.
And what's the capital theta?
That's the Heaviside theta function. So this this integral, it gives you 0 when delta is negative, and it gives you this result when delta is positive. So we see again that the crossing kernel will give you something when the coefficients that you're looking for, or the density of states, is that of heavy It's in the heavy regime. Which is very useful because that's what we're interested in. We're trying to understand what do these heavy coefficients look like, or the heavy rho look like in terms of the light spectrum or the light coefficients. So it will be useful to write this expression from just looks. It seems like I just wrote an H and an L, but let me explain what I mean. So I want to write, like I said, the heavy coefficients in terms of an integral over this crossing kernel multiplied by the light part of the density of states. So again, here rho heavy, you should think of it as just the density of states, but cut off at delta equals to 0. And rho light is the density of states, but it only includes the negative discriminant or light states.
You just go to the beginning of it. Correct that A coefficient on the gravity side. That only depends on the massless fields or the light fields, and then
yes.
Gravity. Right, so that connects to light.
Yeah, exactly. Very good. Now, this equation, if you insert these orange definitions, it's not quite correct. It's not quite true because I've just cut off half of this equation, and you should write plus that same contribution, but now from the but now with rho heavy also in the integrand. But it turns out that this already is a very good approximation once the energy and the J becomes large. And you can show that by taking the ratio of the exact coefficients computed by the Rademacher expansion, and you divide it by rho heavy computed in this way as an integral over rho light. And you'll find 1 plus terms that are exponentially suppressed once the corresponding discriminants are large. So we found a way to encode the S transformation in a sort of coarse-grained way that is easy to work with, but that also gives results that approximate the exact coefficients of the Jacobi form. Very good. So now let's try and understand what do those heavy coefficients look like once we use this crossing kernel business. And for a generic weak Jacobi form at fixed index, fixed t or fixed delta 0, the coefficients in the regime where delta is parametrically large are given as follows. This is basically the same as what I showed before when I talked about the Rademacher expansion. And in CFT terms, this is just the Cardy behavior that you see at high temperatures. And you can see that explicitly once you make the replacement of delta 0 to central charge over 12 and delta to E, then you get exactly the Cardy formula. But once we incorporate lessons that we can learn from AES CFT, we can also find black holes and this Cardy type behavior at intermediate temperatures or at intermediate values of the discriminant compared to delta 0. So let's look at that. The first gravitational constraint that we impose is having a so-called large N limit. In gravity terms, that means that you can write a semi-classical expansion. And in our language, that corresponds to taking the index or delta 0, which scales like the index very large. And then it turns out that the Cardy regime can be extended to these intermediate temperatures if the light spectrum is sufficiently sparse. And what I mean by that is that the light spectrum scales exponentially with delta minus delta 0. And this condition was first written down by Hartman, Keller, and Stoika. Now we'll also refer to it as the HKS condition. And it was written down explicitly for weak Jacobi forms by these people. And what they showed is that if this sparseness condition is satisfied, then indeed I can extend this Cardi behavior all the way down to intermediate values of delta, where delta is comparable to delta 0. But then what about the logarithmic corrections that we're hunting for? In order to find those subleading corrections to this leading order exponential behavior, we use the sparseness condition in this equation that we derived before. And once you do that, you can analyze the integral via a saddle point approximation. And for simplicity, I will restrict to weight 0 weak Jacobi forms, but it's very easy to generalize, and there's no conceptual difficulties if you want to do that, but it makes the equations look a little bit more clean. And you can do that. Once you go through that computation, you find two different regimes. The first regime we call the universal regime, which is the same regime that showed up in this HKS condition. And in that regime of parameters, the coefficients are approximated well by this expression here with approximation sign. I mean that I've discarded order 1 factors, but everything that scales with delta and delta 0 is there. And so again, we see the leading order exponential, and then there's some logarithmic correction to that that depends only on this function that I called rho naught, which can be interpreted as a ground state degeneracy. And so in this universal regime, the logarithmic corrections don't depend very heavily on the details of the light spectrum. You only need to count how many ground states there are, and then you know what the logarithmic correction to the leading order Cardi behavior is. Secondly, we find that in some cases, you can extend this universal exponential Cardi behavior even further, all the way down to a regime that is parameterized in this way. Here there's a new parameter alpha showing up that's always less than 1. And the way that you can think of alpha is by parameterizing the light spectrum, or rho light. The way that we parameterize it is by writing the ground state degeneracy, and we introduce functions g and f. G and f are functions of the energy and this new variable that I call a. Sorry, there's a lot of variables floating around. But a is just a shifted charge where I've shifted the charge such that a is equal to 0 at the ground state. So remember that at the ground state, j was equal to plus or minus b. But in order to parameterize the growth, it's easier if the ground state is at 0 for the variables. So indeed, a is a shifted charge, and this parameter alpha, it shows up in the exponential growth of the light spectrum. And this new non-universal regime appears when the light spectrum grows slower than linearly in the exponential. So this is a stronger condition than the HKS condition that we saw before. All right, very good. So that's how the non-universal regime, what the non-universal regime is. And already from just defining the non-universal regime, you can see that it depends heavily on precisely what are the details of row lights. Right, so like I said, the logarithmic correction depends very sensitively on the precise form of the light density of states. And as an example, we consider alpha equals 1/2, and we take f and g to scale uniformly for large lambda. And that means that it doesn't matter whether I take E or A large, the growth behavior will be the same. This is an example that will come back throughout the talk. So what that means is that once I take the variables or the arguments of f large, again with this scaling parameter lambda, we will see a square root type behavior. And similarly, when I take the variables of g large, which is the polynomial, which encodes the polynomial growth of the light spectrum, I will parameterize that with a parameter called omega. Very good. So we have to be very precise about what the light spectrum looks like. But once you do that, you can run through this saddle point approximation and find an asymptotic expansion for the coefficients in this non-universal regime. And for this value of alpha, the non-universal regime looks like this. There's again the exponential growth showing Cardi behavior, and there's a logarithmic correction that depends on both rho 0, the ground state degeneracy, but now there's also explicit dependence on the polynomial growth of the light spectrum. And so you need very precise details about the row lights in order to understand the logarithmic correction in this regime. Very good. That's all that I wanted to say in this part. So now let's move on to some examples, and they will show up in the context of symmetric product overfolds. So to validate and apply our techniques that we've just worked very hard to obtain, we need families of weak Jacobi forms that satisfy the gravitational conditions that we discussed before. So we need families of weak Jacobi forms where we have access to a limit where we can take the index or equivalently delta 0 large. And the way that you can do that is to look at some grand canonical partition function where you include a new variable called sigma, which is the conjugate variable to this index. And the idea is that when you write that as a Fourier expansion in sigma or t, that the coefficients are weak Jacobi forms of some weight and index t. So in that way, you obtain a power series of weak Jacobi form of increasing index. And you can access these large t forms. And we can construct such families via symmetric product overfold. And the way that you can think about that is by their relation to usual supersymmetric CFTs. Any supersymmetric CFT is related to a weak Jacobi form by looking at this index of VPS states that I wrote down earlier. And once you take a symmetric product orbifold, so you take n different copies of such a CFT, and you orbifold by the symmetric group that acts by permuting those different copies, you obtain a new CFT, which again is associated with the new weak Jacobi form. But now that new weak Jacobi form will have a larger value of the index. So in practice, the way that it works is that you start with your favorite weak Jacobi form. I've done this for weight 0 and of index t0. It will have some coefficients, just like the entire talk. And then I write down this grand canonical partition function where I sum over the weak Jacobi forms associated to the symmetric product overfold of that original.
So each Jacobi form in the sum, each form behaves differently, right? So how does the whole sum behave?
Right. So that's the beauty. Very good question. Very well timed question.
Right.
So there's this result by Dijkgraaf, Moore, Verlinde, and Verlinde, who showed that you can write this grand canonical partition function as a product over the charges. Now there's an extra charge M that's related to T very closely. And again, N and L. And what shows up is just 1 over some type of whole structure. And the coefficients that show up there are the coefficients of the original weak Jacobi form that you started with. And so the idea is that you can access the data of any weak Jacobi form that shows up in this sum by working out this product and extracting out the particular value of the particular power of n that you're interested in. So this gives us an accessible way to find weak Jacobi forms that have such a large t or delta zero limit. And this product formula will turn out to be very useful, I think, on the next slide already. The coefficients of this grand canonical partition function, I can write them down as an inverse Laplace transform, like we've been doing the whole time. And it was shown that any family of weak Jacobi forms that I construct in this way satisfies the sparseness condition by HKS. And so these indeed are weak Jacobi forms that we can apply all our techniques to. Right, like I said. And there's also a closely related construction called an exponential lift. I'll not talk about it, but you can do everything there as well. Moreover, we can explicitly check the results that we got using the crossing kernels by computing this contour integral directly. And the way that you do that is to insert this DMVV formula, so this product structure in this equation. So instead of Z, you write this product of 1 over 1 minus e to the blah, blah, blah. And then you can evaluate one of the contour integrals using the residue theorem, because it's just a product of poles, basically. And you have to do a lot of tricks. The computation is a bit subtle, but once you deform the contours, you approximate the integral by the most important pole in the regime that we're interested in. We obtain this expression on the bottom. And I'm not expecting you to understand precisely what's going on, but it was realized way before we were doing this project that precisely this combination of functions and numbers, that encodes the light spectrum of these weak Jacobi forms generated by symmetric product overfolds in the large n or large index limit. Moreover, this equation, once you do an inverse Laplace transform on this thing we call phi infinity, you get exactly one of the equations that we wrote down before in the crossing kernel derivation. So it should come as no surprise that we can rederive those results in this setup. And the way that you do that is you carry out the remaining 2 integrals by a saddle point. And again, we find that the results agree precisely. For symmetric product overfolds, the ground state degeneracy is given by this expression, which you can find very easily using combinatorics. And this C naught is the ground state degeneracy of the seed Jacobi form that you started with. The way that you find it is by just figuring out in how many ways can I redistribute these ground states over all the different copies. And it scales like that. And this omega, which is the growth, the polynomial growth of the light spectrum, it's given by this combination of coefficients of the seed. Again, there's the ground state that shows up, denoted by B0, and then the 0, 0 coefficient is also important here. We find, again, a universal regime. Here I filled in the way that rho 0 scales. And it matches precisely. And there's a non-universal regime as well. We are precisely in the case that I was advocating for before, where alpha is 1/2, so the light spectrum grows with the square root of the exponential, with the exponential of the square root. And there's this universal growth in terms of the different charges. And this is precisely the result that you would expect from the crossing kernel analysis. And now the logarithmic correction, again, depends both on this omega and on the ground state degeneracy. All right, very good. We're almost there. We're now ready to compare to gravity and really finally understand what this A graph is doing. Let me remind you, there are two different contributions that determine a graph. There can be zero modes coming from isometries. In 4 dimensions, they're given by this expression. The -6 comes from isometries of the metric, and the 8 comes from gravitinos. And in 5D, the zero modes depend on the number of vector multiplets. And there's local contributions coming from massless fields that you compute by a heat kernel computation. In 4D, they depend on the number of supersymmetries and the number of vector and hypermultiplets, whereas in 5D, or in any odd dimension, the heat kernel vanishes. So that's how this number A graph comes about in gravity. And now let's look at some specific black holes to see whether we can explain this thing from the Jacobi forms as well. So the first setting, or the first example, is that of quarter BPS black holes in 4D n equals 4 supergravity. You can obtain these black holes by compactifying type 2b supergravity on K3 times T2. In this case, the logarithmic correction to the area term vanishes because there's a very subtle cancellation between the local contributions and the zero modes. And I should emphasize that this computation is quite subtle. And in this setup, the microscopic description is given by the exponential lift, which for our purpose, you can think about as the symmetric product overfold of this weak Jacobi form of weight 0 and index 1. That is the index associated to a nonlinear sigma model on Kähler 3 manifold.
Can you just say what the subtlety you're referring to was? You gave formulas for the things what are things.
Well, it's just computing this heat kernel that's difficult in gravity.
Oh, okay. But you give a general formula for it. So is it plugging in? I mean, it was everything.
Yeah, for us it's just plugging in, but the way to get that to get those numbers to plug in is a complicated computation in gravity that I didn't do. Welcome. And one crucial part in relating these gravitational entropies to things coming from the microscopic description is understanding what is the relevant scaling that I should look at in these weak Jacobi forms. And since we're in 4D, the area will scale with lambda squared once I take all the charges to be large. And on the microscopic side, or on the Jacobi form side, that translates to both the index delta 0 and delta to also scale quadratically with lambda. And so from that, we can see that we're in the universal regime where delta and delta 0 are similar. And in that case, the logarithmic corrections were very simple to write down. They only depended on the ground state degeneracy. Here I wrote the equation in a slightly different form. But so all we need is to understand or to look in this particular Jacobi form, what is the first coefficient that shows up. That coefficient is completely fixed by supersymmetry and it's equal to 2. And so once you fill that in into this equation, you find precisely 1 minus 1, which is equal to 0. And so we match the results from gravity. But again, to make, once again, reinforce this point, on gravity, this was a difficult computation to do. While on the Jacobi form side, the result is fixed by symmetry. There's nothing there to do. It's trivial. But that's not always the case. For example, in the case where we look at the BMPV black holes that show up in, that are quarter BPS black holes that show up in 5D n equals 4 supergravity. These black holes, again, can be obtained from type 2b supergravity by compactifying now on K3 times the circle. And in this case, since we're in odd dimensions, the local contribution to the logarithmic correction vanishes because of the heat kernel. But there are some zero modes, and they lead to a logarithmic correction of -4. The microscopic description in this case is given by the symmetric product orbifold of the same Jacobi form as before. This thing that describes a nonlinear sigma model on K3. And in this case, the relevant scaling is such that the area scales with lambda to the 3/2. And on the microscopic side, it translates to delta 0 scaling with lambda squared, while delta scales linearly with lambda. And so in this case, we are in the non-universal regime, where delta 0 is parametrically larger than delta. So in this case, the logarithmic coefficients are given by these expressions that we saw before. And for this Jacobi form, the ground state degeneracy is still equal to 2. But now we also need this second coefficient, C00, which is equal to the Hodge number of K3. And it's 20. And once you fill that out in this equation that I wrote before, again, we find complete agreement once you take your 3/2 and put it inside the logarithm to have there the area. And so again, we are able to precisely match the gravitational results and also understand precisely what are the states that are responsible for this -4 from the microscopic point of view. And also here we're sort of kind of in an opposite situation as before, where now the gravity computation is trivial. It only depends on zero modes. You just count the symmetries. While on the microscopic side, the computation is very subtle. You have to very precisely parameterize the light spectrum, et cetera, et cetera. All right, very good. And then there's one final type of black holes that we studied. Here, both sides of the computation are very complicated and very subtle. And I'm just going to give you a very brief overview of some of the things that are going on. But yeah, I think one could give a whole seminar about just these black holes. So I'm going to be extremely brief. But let me nevertheless show you a little bit how it goes. These are half BPS black holes that show up in 40 n equals 2 supergravity. They can be viewed from M theory on a Calabi-Yau 3 times the circle. And the entropy is given by this expression that was found by Suzanne. And here the logarithmic correction, it depends on the details of the Calabi-Yau, which encodes the number of vectors and hypermultiplets that appear in the theory. And it was argued by Suzanne that this logarithmic correction agrees with the OSV formula, or OSV conjecture, that says that the black hole entropy can be computed by evaluating the topological string partition function. And the relevant counting formula for that is a weight -1 form of rank NV. And that means that this modular form, it has multiple charges. Throughout the talk, we've had one charge to worry about, but now there's NV charges. And so we have to generalize all our techniques, which is something that you can do. It's a little bit subtle, but conceptually it works the same way. And the light spectrum can be factorized into a contribution that comes from supergravity and a contribution that comes from non-perturbative M2 branes. And the supergravity part of that formula, it simplifies. It localizes on the ground state value of the charge, of all the charges, Bi, and the only dynamical or the only value that it depends on is the energy or tau. And it turns out that in the limits of large index, only the Z subgraph part of the light spectrum is important. At least that's the orders that we are interested in. And that light spectrum, it can be parameterized in this way. This is also very subtle. In the literature, people don't really agree on what it should look like, but to the best of our abilities, we think this is the correct parameterization. Where here you see a few parameters showing up. There's a chi, which is the Euler character of the Calabi-Yau, and there's the Riemann zeta function that shows up. And here we're in a very different situation as before. The light spectrum only depends on n. And also the power that shows up in the exponent is different. Now we have alpha equals to 2/3. And also, omega is given by this combination of numbers. And there's a ground state degeneracy that's linear with delta 0. And we're back in 4D, so the relevant scaling is that the area scales quadratically with lambda. And on the microscopic side, the relevant scaling regime is that delta 0 scales cubic with lambda, while delta scales linearly. And that means once you incorporate that with the alpha equals 2/3, that you're all the way at the edge of the regime of validity of the non-universal regime. So you're really pushing all the way to the end of the sort of regime where you have this universal leading order behavior. But we were able to show, or one can show, that the logarithmic corrections are robust under going all the way to the edge of this regime. However, the leading order area term starts to get corrections. So the result is as follows. Here I wrote the logarithm of the coefficients. First, there's this thing that looks like the area, but it's not quite the area because there's an extra factor of zeta there, which is an order 1 number that we can write down in terms of the light spectrum. But you get some order 1 correction to that leading order term. But the logarithmic correction is okay. It looks like this in this situation. And once you fill in the value of omega and you use that the Euler character is given by this expression in terms of the number of vector and hypermultiplets, we again match precisely the logarithmic correction computed from gravity. So again, even in this way more subtle and way more complicated way, our techniques of using crossing kernels were powerful enough to precisely point where this logarithmic correction comes from on the microscopic side of the theory. So I think that's really a really cool result. All right, so that's basically all that I want to say. Let me summarize very quickly. We studied the asymptotic behavior of Fourier coefficients of weak Jacobi forms using this technique called crossing kernels. Combining that with conditions coming from ADS-CFT, we found an extended Cardy regime and logarithmic corrections that depend sensitively on the light spectrum of the theory. Our method can be validated in the setup of symmetric product overfolds. And in this way, we were able to give a precise microscopical interpretation of the logarithmic corrections for certain BPS black holes. So that's it. Thanks for listening.
With the dot in your formula,
right?
Does that mean that the limit for large A is finite, or is that something you can see from?
Sorry, is there
the model form?
What equation are you referring to?
Well, you know, your basic.
Oh, this one.
Yeah, that is right. The dots.
Right.
Does that mean that they are?
Yeah. Wherever I wrote plus ... there are things that are exponentially suppressed in either delta or delta zero on the weak Jacobi form side.
So in terms of
A? Right, they will be, they can still be exponents, but they will be down in A over 4G.
You're saying there's no order one term?
Right, but that compared to the leading order term, that's exponentially suppressed, right? That's what I mean, sorry. When you take the ratio of those two terms, you will find something that goes like e to the minus A over 4G.
I guess my question simply was in the large A limit.
Yeah, they go away.
Oh, they go away.
Yeah, it might be an order one thing, but the area is large, so no.
You say exponentially small, I was thinking e to the minus A, not order one. That's how it is.
Well, compared to the A over 4G, I would say that that's exponentially suppressed.
But that's some result.
It's some.
That's some result due to supersymmetry, the one loop direction of the kilometers is that. I mean, some of it is due to massless modes.
Yeah.
Stuff. So in general,
I don't know from the top of my head. I don't know from the top of my head. I would have to look it up.
And you'll work this is out for non-supersymmetric black holes, right? So it's like a one loop determinant for massive fields.
Right. Yeah. Yeah, I don't know exactly what would show up in those dots when you do that. One loop determinant. But yeah, I hope I answered in some way.
Zeta, go back to the
Zeta, yeah, it's like a combination. I don't remember, but it's like something like the alpha shows up, and then this thing also shows up there. I can show you the exact expression.
What should I think about it from the gravity point?
So what we think that is going on is that in the paper where Suzanne is computing these logarithmic corrections, he's evaluating the path integral in a regime where also the area term gets corrections, but he doesn't discuss that area term.
Not problem with the area terms too.
Yes, I thought so. Yeah, so I've talked to a lot of people about that, and they were all saying like, yeah, the equation that he uses, you shouldn't use it there because the area term gets corrected. But again, we can show that the logarithmic corrections are robust, even in this.
It's perfectly possible that the logarithmic corrections are correct, even if the area term is correct.
Yeah,
but it's weird that it does. But
well, I think it's basically just saying that M theory in the semi-classical regime is hard, and even thinks that.
But I'm asking, is there even a guess of what might give rise to such correctness?
From the gravity.
From the gravity point of view, the perspective is still that there shouldn't be any corrections.
Well, I think the point where you can evaluate the path integral is a point where you're not strictly in the semi-classical limit. However, the thing that people use is that this thing should be robust even in that limit. But what I understand from these papers is that that's not quite the case, and this area term starts to get corrected. But yeah, I'm no expert on M theory. Anything related to the gravitational computation.
Gravity computations.
Yeah.
Like low energy gravity. And theory is only in the background.
Yeah, I would have to look again at the paper.
Any questions for Suzanne? Monitor sometime after the talk, she'll be around for
A long
this year
time.
now. Yeah, a long time. Any other? Let's think of.
No, cool. Don't know.